So good morning everyone. So hello and welcome to another lecture, in fact lecture number 5 of this course on line commutated and PWM rectifiers. And today we will talk about the harmonic analysis of rectifier input current. So we are basically now in week 2, and here we are covering the multiples. We will cover multiples rectifiers, but before that, at first we are going to cover this input current analysis and THD and the power quality issue. Okay, these things we will first cover as part of week 2, and then we will shift to one of the solutions, which is the multiples rectifiers, and subsequently we will start with other types of power converter based solutions like these which are shown here. Okay, so let us quickly recall from week 1 that we studied the diode bridge rectifier and the thyristor bridge rectifier, and two representative figures have been shown here, and on the left you can see that the full bridge single phase thyristor rectifiers. And the important thing, and as I had mentioned several times, that the current, the source current here, this is the source current waveform, and we can see that this source current waveform is a square wave, right? So the thyristor rectifiers, the single phase thyristor rectifiers, although they are very good in changing the output voltage, they can vary the output voltage, and therefore if we feed a motor, suppose a DC motor, then we can change the speed and of the motor. But then one of the problems is that this source current is absolutely non-sinusoidal. It is square wave current. Similarly, if we see the diode bridge rectifier, again feeding some form of a constant current load, okay, we see that this source current, okay, this IA current here, you can see this is a quasi square current, okay, which is full of harmonics, right? And this is not only true for motor drive load, okay, capacitive loads are also responsible for responsible for a severe distortion of the input current. And here you can see, suppose we have an RC load. This is typically used for producing some form of an output voltage, right? So here you can see that the output voltage here V0 is having a DC value here, okay, and some ripple, okay. So but the disadvantage or the problem or the challenge is that this source current here, this IG, this is the source current here, IG, this source current is having a huge amount of this, it is spiky in nature, okay, and it is having a huge amount of harmonics in this source current, okay. It is far away from a sine wave, okay. As I told you, the grid always seeks, or the grid always wants, that all the loads should draw sinusoidal current from the grid, right? So we'll see later what does this term means. This term is actually THD, means total harmonic distortion, which is actually 240% here, which we obtained from simulation. So the total harmonic distortion is a figure, okay, it's a quantitative measure of the harmonic distortion. You'll see about it in this lecture. Yeah, when we have a higher power, okay, even with a 3-phase diode bridge rectifier, you can see here that the output voltage is nice, okay, which is having a steady DC voltage with a small ripple over it, but the input current here, you can see this input current here, okay, so this is IB here, so the input current here is exceedingly it's full of harmonics, right? And the harmonic distortion is about very high here, okay. So we understand that whether it is a motor load or whether it is a capacitive load, in both the cases we find that the input current which is drawn from the grid is highly non-sinusoidal in nature. Okay, so let us take the case of this quasi square wave current, which is most common, right? So we will analyze this input current of the rectifier, and there are some standards like this IEEE 519 standard, and this standard actually puts a limit on the maximum amount of harmonic that can be injected into the supply. Okay, so if you build a product based on, suppose you build a product which has a diode rectifier at the front, right, and this diode rectifier and you want to sell this product in the market, then you have to comply with certain standards like IEEE 519 or IC standards. And if you do not comply with these standards, you will not be able to sell this product in the market. Okay, so it is important that we understand that the importance of power quality or the importance of good input current which is being drawn from the supply. So if we just look into this IEEE 519 standard, okay, I have copied from the standard document which I have taken from this one, and you can see here that these are the harmonics. Okay, so these are the different harmonics and their percentages in the total current. Okay, so you can see here that the total harmonic distortion here for all the harmonics should be less than 5%. Okay, so this standard says that at PCC means point of common coupling. Okay, so at PCC the users who are drawing current from the utility grid shall limit the harmonic currents as shown, which means that you have a grid here. So okay, this is a utility grid and you are one customer. Okay, this is you are one customer, and the current which you draw here, okay, that current should have a total harmonic distortion less than 5%. Okay, this is the as per the standard. Okay, so this is the point of common coupling. This point is called point of common coupling because at this point you are actually basically other customers are also connected. Okay, so at this point of common coupling, so the current which you are drawing as a customer, you should not cause more than 5% THD. Now you can compare this value of this 5% with respect to some 180% or something which we had just shown in the previous slide. So with those kind of very peaky currents, you will not be able to put this equipment here. Okay, you will not be allowed to put this equipment into the grid. The grid will not allow you, and you will be not following this kind of a standard. Okay, so therefore it is important for us to actually improve this current harmonic profile. Okay, and before we do that, we have to first understand these terms: what is total harmonic distortion, what is distortion factor, what is displacement power factor, etc. This we will cover in this lecture, and then we will start seeing some of the solutions in the next lecture. So let us first understand a little bit about what are the properties of this kind of a quasi square wave current which is drawn by these rectifiers. Okay, so if you analyze the basically we are analyzing the harmonic content in this kind of a quasi square wave current which we are drawing from the grid into the equipment. Okay, so this is generally a periodic waveform, and if you do a Fourier series analysis of this quasi square wave current, we can write that this function to be a0 plus an cos n omega t plus bn sin n omega t. This is a very standard form and of Fourier series analysis. Okay, and you can just recall how this comes. Okay, in this case a0 is of course 0 because we do not have an average, the average value is 0. Also we note that this waveform has an odd symmetry, that is f of theta is equal to minus of f of minus theta, or f of omega t is equal to minus of f of minus omega t. Okay, so when you have this odd symmetry, then basically an terms vanishes. Okay, so this is one property, and I would if you have forgotten these things, kindly recall it from your basic mathematics course. This waveform has also half wave symmetry. Okay, so which means that f of omega t plus pi is minus of f omega t. So therefore now we have only odd terms in Bn. So first of all, we do not have the an terms. So an terms we do not have this one. A0 is not there. We have only the Bn terms, and even in Bn, because of this half wave symmetry, we have only the n equal to odd terms present. So what is the magnitude of this Bn terms is equal to, which we can see, 4 by 2 pi alpha to pi minus alpha, because we are going to integrate from here to here. Okay, because of half wave symmetry we do not need to integrate the full cycle, and so therefore we just integrate and we get this as the magnitude of the harmonics. So ft can be now written as summation of 4i by n pi cos n alpha sin n omega t, and this is valid for all n equal to odd. Okay, so we will have in this quasi square waveform, we will have n equal to, the fundamental is there, third, fifth, seventh, ninth, all these harmonics will be present. Okay, and so these are the harmonics. Now one thing is that I have not mentioned the third and ninth here. The reason being that generally if you have a star connected transformer at the input of this kind of a diode rectifier, the third harmonics generally get cancelled. Okay, because of the presence of a star connected transformer, right? So what goes into the supply, suppose whenever you have this kind of high power rectifiers, we generally supply from the grid via an isolation transformer for safety reasons, and also for stepping up or stepping down the voltage, generally stepping down the voltage. And that transformer is one side is star connected, and therefore it will restrict the third harmonic or the triplen harmonic currents. So therefore the current which is going into the grid will be having all the odd values of like 5, 7, 11, 13, these harmonics. So in general we can say that 6n plus minus 1 harmonics are present in this waveform where n is equal to odd. Okay, and another thing to observe is that the magnitudes of these harmonics decrease in proportion to 1 by n. Okay, sorry, the magnitude decrease in proportion, so it is basically it is this ft, the magnitude of ft is proportional to 1 by n. Okay, so that is what is coming up in the equation. So here you can see here that you have this fundamental, and the fifth harmonic is 1/5 of the fundamental. Okay, so if this is 100%, fifth harmonic is 20%, and then seventh harmonic is 1 by 7, 11th harmonic is 1 by 11, like that. Okay, so now we will introduce two terms here. Okay, distortion factor and THD, as well as the displacement factor. Okay, so let us, so these factors or these terms will be used to quantify. Okay, so we want to quantify the effect of the harmonics. Okay, the first term that we are encountering here is called the distortion factor. So distortion factor of input current is defined as the ratio of the RMS value of the fundamental component to the total RMS amplitude. So here I1 RMS, the fundamental RMS divided by the total RMS value. Okay, so the RMS value of the fundamental inside that waveform with to the total RMS value of the waveform. So let us find out for this quasi-square waveform of input current, okay, what is the distortion factor. So at first we find out the RMS value of the input current, right? So this is the denominator of that distortion factor. And so how do you get the RMS value? Basically here the values is 0, okay, so we don't need to integrate. We basically have to integrate from 0 to pi because we are squaring it, so we do not need to integrate this section from pi to 2 pi. Okay, we just need to integrate from 0 to pi. So that is what we have done, 0 to pi, and even there also we do not have any value here, 0 value here, and so we will integrate from pi by 6 to 5 pi by 6, right? And so, and the magnitude of this is I square, id. So here this magnitude is id, so id square into d theta. And so when you do this calculation, this will come out to be 0.816 id, right? So this is the RMS value of the input current. What is the peak value of the fundamental? Okay, so we have seen already in the previous slide that this is the fundamental. Okay, this is the fundamental. So if I put n equal to 1, okay, if I put n equal to 1 in this equation, we get the peak value of the fundamental, right? So we go back here, so we have put this n equal to 1, so 4 id by pi cos pi by 6. Okay, so this is the peak value of the fundamental inside this. So this peak, the fundamental is here somewhere. Okay, right? So this is the fundamental peak, and therefore the RMS value of the fundamental I1 RMS is 1 by root 2 times I1 peak, which comes out to be 0.78 id. So if I now apply the formula of the distortion factor, then we see that it is equal to RMS value of the fundamental divided by the RMS value of the total waveform, and this therefore comes out to be 0.955. So this is the distortion factor of this quasi-squared waveform of the current. Okay. Of course, this analysis, you can, why we have taken this value, this is very common. Okay, we have seen this kind of a current waveform in the diode bridge rectifier, even in thyristor rectifiers also. Okay, now the next term that we will introduce is called the THD, total harmonic distortion. So what is the THD? THD is the ratio of the RMS value of all the harmonic components to the RMS value of the fundamental. So basically here you can see THD is equal to, right, the RMS value of all the harmonic components, H equal to 2 to n. Okay, so RMS value of all the harmonic. So here you can see I2 square plus I3 square plus I6 square up to IN square. Okay, so RMS value of this one, right, and divided by the RMS value of the fundamental, right? So therefore this is the definition of the total harmonic distortion, or THD, and therefore we can say that this 1 plus THD square, okay, if I just put it 1 plus THD square by using this equation, is 1 plus this value divided by I1 square. And now you can see that if I take this one, basically the numerator now becomes I RMS square, because I RMS is nothing but I1 square plus I2 square plus I3 square up to IN square. So therefore this is I RMS square divided by I1 square, which is nothing but the inverse of the distortion factor squared, right? So therefore this relation exists between the distortion factor and the THD. In fact, this is like distortion factor is equal to 1 by root over of 1 plus THD square, right? So this is how the distortion factor and the total harmonic distortion, these are related to each other. So in the given example of the quasi-square wave current, so THD will become equal to 31%, okay, 0.31 or 31%. Either you express it in a decimal fraction, or THD you can express in percentage. So suppose you can take an example. So suppose if you say that there is an equipment whose input current THD is 50%. Okay, so then we can say that since you know that this THD is 50%, so IRMS will be root over of 1 plus THD square into I1. So which means that this equipment, okay, in this equipment the RMS current is 12% more than the fundamental RMS current. If you just plug in into the value, so THD value is 0.5 square if you do it, so you will find that the RMS value, this value is 1.12 times I1. Okay, so which means that the wires which is carrying the current into this equipment, the RMS value of that current is 12% more than the fundamental RMS current. Remember, the fundamental RMS current is only responsible for the active power being delivered to the load through that wire. All the rest of the harmonic currents are useless. Okay, they have no use, they do not contribute to the load power delivery. But the losses in the conductor, okay, the losses in the conductor is proportional to the RMS value of the current. So therefore we will have much more losses in this case, because these useless harmonic currents which is flowing through this conductor is going to create additional losses, and we would, of course, we would not like to have them because it will have a temperature rise, right? So these additional harmonics are not useful in transferring the power but causes additional losses. So now we introduce another definition which is called the input displacement factor. Okay, so displacement factor DPF of input current is defined as the cosine of the angle between the fundamental component of AC input current and the corresponding line neutral voltage. Okay, so it is basically DPF is nothing but the cosine of the angle between fundamental component of voltage and the fundamental component of the current. Okay, so both the fundamental quantities only. Okay, so this is the factor which is actually causing the power to be delivered from the source to the load. So the power is equal to V1 I1. So this is the fundamental component of voltage RMS value times the RMS value of the fundamental component of current times the DPF. Okay, so this is the definition. So now the input power factor, the definition of the power factor, okay, the definition of power factor, when you have a lot of harmonics in the input current, the definition of power factor needs to be modified. Okay, and so how do we define the input power factor? The input power factor is defined as the ratio of the total input power to the total RMS volt ampere, which basically means the input power factor is the power in, okay, which you are feeding to the equipment or to the load, divided by the RMS total volt ampere RMS value. Okay, so you have a source and you have a load. How much is going into the load is this P in, how much power is going to the load is P in, and V RMS times I RMS is the input RMS voltage times input RMS current, right? Suppose we assume that the input voltage or the grid is purely sinusoidal. This is typically the case. Most of the time the grid is very close to sine wave. So then V RMS is equal to V1. Okay, RMS value of the grid voltage is almost purely fundamental. So V1 is equal to V RMS. So therefore the power factor is P in divided by, so this value then becomes P in by V1 into I RMS, right? Because we have said already that it is V1, and so this one can be written as P in by V1 into 1 by RMS. So P in divided by I1 here, and I1 multiplying both numerator and denominator by the same I1, we see that power factor is equal to DPF into DF. Okay, so which means that in presence of harmonics, the DF, okay, the DF has a role to play. If there are no harmonics, DF is equal to 1. Okay, So then in that case PF is equal to DPF. So power factor and DPF, which is the conventional definition of power factor, which says that the it is the cosine of the angle between the input voltage and the input current. But this is only true if there are no harmonics present. In this case, we have a harmonics present in the input current, right? So therefore, the power factor definition has to be modified. And in the presence of harmonics, power factor is equal to dPF into dF. Okay. So therefore, we see that as more and more harmonics are getting injected, okay, or which is being drawn by this power electronic converter or the power electronic rectifier, okay, the more and more it is harmonic, the harmonics are drawn, this distortion factor becomes poorer and poorer, okay, and therefore the power factor will also go down, okay. So this is one of the drawbacks of this kind of a rectifier, okay, that the power factor goes bad, right? So yeah, so you can see here, if the input voltage is purely sinusoidal and the current is shown as we have seen in the quasi square waveform, the distortion factor was 0.95, hence and the dPF is equal to 1, right? Why dPF is equal to 1? Because this waveform has this is the fundamental, okay, this is the fundamental quantity, and the angle here is 0, okay, between the fundamental voltage and the fundamental fundamental current. So if you remember 4I by n pi cos n alpha, and there was only sine n omega t, right? So there was no phase shift, okay, so there was no phase shift, so there was so this has the dPF is, therefore the dPF is equal to 1, right? So therefore the power factor is 0.95. Now you can see here that if the distortion factor would have been 1, right, if the distortion factor would have been 1, then the power factor would have been 1, but now we have a lower power factor of 0.95 because the distortion factor is no longer 1, it is less than 1, okay. So therefore now you see this is a slide which I had shown previously in thyristor rectifier, and in case of this thyristor rectifier we are drawing a quasi square waveform, okay. If you can recall, this is the source current waveform, here is the source current waveform, and in this source current waveform, as you can recall, that when we start firing the thyristors like this, this is the firing angle of the thyristor, we can actually change the output voltage, but what happens at the input side is that, okay, the input current, which is a quasi square wave, that input current is basically shifting with respect to the input voltage, right? So therefore this shift is denoted by these phasors. The phasors are between the fundamental voltage, the fundamental grid voltage, and the grid current which is drawn by the thyristor converter. So this basically this angle is shifting here, okay, and this angle yeah, so this alpha, this is shifting here, right? So this here the dPF is equal to cos alpha, right, because this is the angle. So here is the fundamental component of the, okay. So here we see that the dPF is equal to cos of alpha, right? So here alpha is equal to 0 degree, okay, and here so this is the alpha actually, okay. So here the dPF will be equal to cos alpha. So which means as we go on changing the firing angle of the thyristor, we are going to change the output voltage, but what happens at the input side is that the dPF is basically going down, okay, the dPF is falling, okay. It can start, so when alpha is equal to 0 degree, so it starts from alpha, dPF starts from 1, but it then goes down progressively as we increase the value of the alpha. Of course, if the dPF is falling, the power factor, which is equal to dpf into df. The df is constant. The distortion factor of this quasi square waveform is constant, but the dpf, this dpf is falling, and therefore the power factor is falling, right? So which means that a thyristor rectifier, okay, as it is drawing reactive power, so as it is delivering the active power, for the same active power, if we start changing the active power by changing the value of alpha, then it will start drawing more and more reactive power. Falling of the active power factor means it is drawing more and more reactive power, okay, and the situation will get to worse. The situation will worsen, okay, when we have an increase in the firing angle. So if we go with high firing angle, okay, then the situation will become more, it will become worse, right? So because the alpha value will go on increasing from 0 degree, and then it will go on increasing like 30, 60, like that, okay. So this is one major drawback of the thyristor converters. So let us take a quick small example, okay, where we can find out how are these values. So suppose three-phase diode bridge rectifier is there, which is fed from this 415 volt 50 hertz source and supplies a motor load, and the load current is constant at 10 ampere, okay. So find the average output voltage and the output power to the motor. So what is the average voltage output? Average voltage output, if you can quickly recall, V0 average is equal to 3√3 Vs by pi, where Vs is the peak of the phase voltage, okay, that you have to remember. So therefore Vs in this case is, this is the line voltage divided by √3 into √2, that is the peak of the phase voltage, which comes out to be 338, and substituting this value we get the average output voltage as 560 volt, and multiplying that one with the current, so this times the output current, which is considered ripple free. So output current is considered ripple free, okay. So then this average output current is so load current is constant at 10 ampere, which has been given. So the output power is 5604 watt, right? Now next question is, what is the fundamental input current magnitude? Okay, so first we talked about the output side, and now we are saying fundamental input current magnitude and the input power, right? So let us see. So fundamental input current, what is I1 RMS, okay. So we know that this current is basically a quasi square wave current, which we have seen in the first slide. It was this quasi square wave current. So therefore the fundamental input current I1 RMS is 4 I0 by pi cos pi by 6 times, this is a peak value, here is the peak value, and this is the RMS value, right, 1 by √2. And so this value is 0.78 times I0, and since I0 is 10 ampere, though this is equal to 7.8 ampere. And the displacement power factor dpf is equal to 1, because this is like this thyristor rectifier with alpha equal to 0 degree. So therefore the displacement power factor dpf is equal to 1, and hence the input power, right, what is input power? Input power is input RMS voltage V1 RMS I1 RMS into dpf, right? So this is the fundamental component of the voltage times fundamental component of the current times the angle between fundamental voltage and fundamental current, okay. So this is the input power, right? So therefore this is equal to 3 into 415 by √3, this one, and I1 RMS we have just found out is to be 7.8 ampere, and dpf we have found is 1, right? So therefore the input power is 5604 watt, right? And as expected, we have seen that the input power is equal to output power, because we have assumed that this converter is lossless, it is an ideal converter. So we also got that input output power 5604 watt, and the input power and output power are basically matching with each other. What is the third part of the question? What is the VA supplied by the source? Okay, volt ampere supplied by the source. Now here you have to be a little bit careful. What is the volt ampere supplied by the source? The volt ampere supplied by the source S in is 3 times, because there are 3 phases, V in RMS into I in RMS. Okay, it is no longer simply the fundamental, it is the total RMS values. Okay, right? Now what is I in RMS? I in RMS is 0.816 ID, which we have just few slides back we had derived it, that the total RMS value of the input current, and this will be 8.16 ampere. So therefore the S in is equal to 3 times V in RMS, because the voltage we have assumed to be purely sinusoidal voltage, so fundamental and the RMS values are same, and so 403 into 400 by root 3 into 8.1 is 5865 VA, right? So therefore the input power factor is what? Input power factor is your P in divided by S in. We have found out what this is, the S in, the input VA, and we have already found out what is P in. P in is this one here, we have found it, right? So therefore the power factor is P in by S in will be equal to 0.955. okay, in fact you can check that this will be equal to dpf into df, right? Okay, so the df here is equal to 0.955 and dpf is equal to 1. okay, so this will come, okay, that the power factor is equal to dpf into df, but you can also see the power factor as P in by S in, which will be 0.955. okay, so you can also understand that this I in RMS, which is 8.16, is more than the fundamental current, which is 7.8 ampere. okay, I1 RMS, and so the the extra current is about 4.6%, so the grid will be at a loss to supply this extra current. okay, so we end this lecture at this point, and we will next take up the some of the solutions to improve the harmonics. So we just went through quickly on some of the problems of the harmonics, and then we'll see some of the solutions starting with a multipulse transformer. okay, we end it. Thank you for watching this lecture.